Okay, for next week. So this is the block diagram for a basic linear regulated power supply, right? Which is what we're learning. Pretty straightforward. Everybody got okay with these? Y'all know the function of all those, each section? The other type of power supply we're just going to get a basic introduction to is referred to as a switch mode power supply. Some people call them switching power supplies. Now the problem we have with linear power supplies is they operate over here in the U.S. What's our frequency operating? Now, what are we required to produce EMF for both electromagnetically? Now we need a magnetic field. Wait. Then we need a what? Conductor. And what's the third thing? Relative motion. Should be. Might do that. I'll put it on the test review because that's something y'all should know, right? Like on my PLC class, the first question on the test was, what does PLC stand for? And only 31% got it right. And they're taking the class. Yeah. Controller, most of it's a control, but I just, yeah. The problem is, that right there, is that we're hertz over here and 50 hertz everywhere else, right? Well, what if we can increase the speed of the motion, and that's going to make our transformer smaller. That's going to make our capacitor smaller, and so it's going to become more efficient, right? So one of the things that we can do with we can take DC and we can make anything out of it we want to. And a perfect example is this one right here. So this thing 60 cycles. But with this thing, since it's electronic, I can take that 60 cycles, I can use a power supply to plus and minus DC. And I can be oscillated and make it any frequency I want it to do. So this guy right here goes all the way up to 5 megahertz. All the 60 cycles. After 60 cycles, 5 megahertz, we get it electronically, right? You understand? So we don't have to be oscillated. So that means if I can do it here very easily, oscillators, we can take the AC in. We can do what? We can chop it up, convert it into DC. Then we can use the transformer. Now my transformer is going to be a lot smaller because we can make it a lot frequency. So I can transfer more energy with less windings in my transformer. Right? Does that make sense? Frequency goes up. Transformer has more what we call reactance. So I can use less copper in my transformer. Then I can filter it, right? I can rectify it. I can refilter it now. And then what I can do to control the output is I can change my oscillator, which is pretty neat. Does that make sense? So these guys become a lot more efficient, which means they can be what? My transformers are smaller, my capacitors are smaller, my power supply can be a lot smaller. The big problem is that they generate a lot of electrical noise. There's a lot of filtering. There's a lot of filtering right here because these guys are very, very noisy. So this is called switch mode power supply. The problem is they're normally when these things go, we just replace. So this is one way they can do it. So what we can do is, so the switch is simulating our circuit that's pulsing, right? You understand this simulation don't keep up real fast. So this is electronically what we're doing is we're generating pulses. This is going into the inductor that is going into a capacitor that lacks change. So the inductor gets rid of your low frequency. Your capacitor gets rid of your high frequency. And we can end up with a really nice DC out of this thing. All we got to do is figure out how we cause this thing to do what? Switch electronically. So you could do this. Most switch mode power supplies operate above the human ear, so that way you don't hear them buzzing all the time, and they become more efficient the higher you do it. So I'm using around 15 kilohertz up here for my input. Pretty neat. So this is basically what we end up with a rectifier filter. We have pulse, but normally they use something called pulse width modulation, which is really, really neat. So what are regulators? What are and of course I'm going to use DC up here so we can see it with our meter. Oscilloscope, and I've got my measure DC. Let's move. And then what I have is I have my meter came off. Oops. I disconnected my meter when I was showing y'all those metal things on my. So what your DC devices see this as is they see this as an average. So I have mine on 5 volts per division, so that's about 12 volts, right? Now, what I want you to notice is I'm not going to change the frequency. What I'm going to do is I'm going to change what we call the duty cycle, or change the width of my positive poles. So notice when I make them smaller, the frequency is not changing. See, here's my voltage right here. We're not looking at DC. We're looking at what DC is, right? Understand? And I come over here. This guy doesn't do a good job. The frequency's changing a little bit on this, but pulse width modulation, the frequency is not supposed to change at all. So notice this guy here and this guy here. What we do is we use something called a duty cycle. So this is my frequency change to hair. Let's move this in. Oops, not that one, Rich. This guy. No, that's as low as I can go. This is about what we call a 50% duty cycle. Can you see that? So this is 100 microseconds. That's 100, 200, 300, 400, 500, 600 microseconds. It's not bad. So what we would do is we would, to calculate the duty cycle, we would take the period, right, which would be what? 600 microseconds, right? And then we divide it by the amount of time. That's 300 microseconds. 0.5, we could do what we call 50% duty cycle. And can you see if this is 12, it's actually about 13 volts. At a 50% duty cycle, my DC would be an average of 1/2. So we can calculate or look at the duty cycle, and you should be able to calculate how much voltage my meter would see. So here I've got it high. I've got it high 100, 200, 300, 400, and then low 200 microseconds. It's 400 divided by 600. What would that fraction be? 46. So we could just count. I've got it on hundreds, guys. In fact, it's on tens, but it don't make any difference. I didn't see my decimal point. We could just count divisions. So we got it high, 1, 2, 3, 4, right? You understand? So I'd say 4 divided by 6. And what's the fraction do you get? And then multiply that times 13 volts. Which is about what it is. What's that? Yeah, I would say, look, we're measuring what, 8.46. Because so all you'd have to do is a motor. If I had a 12-volt motor on here, a DC motor, it would run at whatever voltage that was. So this is probably one of the methods now because we can things off. You can very easily do control the speed of a motor, but this is what they're doing with this. What they're doing is the output. If the output is too high, they increase the pulse width, right? And if the output is too low, if it's too high, they decrease the pulse width. If the output is too low, they increase the pulse width. So this is why they use a pulse width modulation. And what's nice about digital is that these devices are either completely on or completely off. How much power is turned off? Because when it's turned on, it's square R. So it's turned on. Light switch shouldn't dissipate. So if I've got an electronic device, I either turn wide or I turn it off. Now, the problem with solid state is that it takes time. So when we look at that, we see it. Yeah, what it's doing is changing the pulse width. it's doing it on its own, right? You understand? That's what the feedback does. So the feedback circuit goes back and tells the oscillator circuit to either increase the duty cycle or decrease the duty cycle. And that's the way these things regulate. That's what a regulated power supply does, right? We don't see the closed loop inside a fixed regulator because it's feedback. We can see that actually are made up of. So what happens on an electronic device is that we look at it like this, right? Now, if this was perfect, same thing, right? Understand? But what actually happens on electronic spread it out, and then my current is going to be this. So when this thing switches on, my current is going to be doing something like this. So here the device is going to be producing still going to have a voltage problem. To the switch average right there, right? You understand? So they'll dissipate a lot less power considering the amount of power they're controlling, right? You understand? But they're still hot. So this is why even if we're using these switch mode power supplies, these transistors are still going to be used. That makes sense. A light switch, it's either on or off. There's really no rise time or fall time. So light switches shouldn't get hot at all. If you got a light switch that's get hot, what does that mean? It's a problem. You just got an power component now. Or something's happened to them. It means you need to replace them. If you got a wall outlet that's getting hot, what does that mean? It's a problem. The wall outlets are supposed to have 0 ohms too, which means you got a problem with your power cord, or you need to replace that. You got bad things inside there. Right? Guys, you're going to run into these all over the place. Well, what's so nice though is that pulse width modulation can take care of even different voltages. So when I look at the power supply on my trainer, I mean, if y'all can read this, I don't know if I can get it close enough for you to read. Focus on it. This guy operates from any voltage. My input voltage can be any voltage between 100 and 240 volts. Because your switch mode takes care of giving you the right output, right? Even though if it's the input's wrong. And this is at 1.8 amp. I'm sorry, this is at the 3.2 amps. 1.8 amps in, 2. And of course the power supply consumes energy too, right? So switch mode power supplies are set up basically they can operate over a longer range of input voltages, right? You understand that? Which makes it pretty neat. For the plug, big companies use the same buy that adapter. You got something that uses a power supply. I don't give an adapter, but a voltage adapter. Basically, it's just nothing. 240 volts. Those are expensive. Those are. I think I bought mine. Here. I didn't need it for this, but. Yeah, but even on your little brick, it gives you the input voltage that's available. Just a switch mode power supply, are, and those are mostly always. They're so dang small. Right? Should have the input voltage. If you got one from Walmart, it might not be. But we talked about. How that moves around, so you need to look at section on those adapters for you. Are you to be able to do what? Those things are in compared to what they do, they don't get that warm. Right? The transistors are either on or off, but unfortunately, where they do have to warm. But if I was to look at a linear regulator, these guys right here, these guys get hot because they're dropping a voltage, right? So fixed regulators, these are linear regulators. And then so get hot, it's rated at 5 amps. You got 20 volts on one side and you got 5 volts on the other, right? You understand? That regulator's dropping 15 volts at 5 amps, right? You understand? That's 55 watts. That regulator will have to do what? Would have to dissipate. So these linear regulators, those outputs are operating on what we call the linear mode. They're acting like rheostats. That's exactly what they do. So when we get into dipole transistors, we'll show you why those things. We have two ratings. We have maximum current flow, and then we have power rating, which you can't see. How to do that? If you see the power rating on these linear devices, so we'll show you that too. It has sheets on it where it says to get much wide rating out of it. Okay. Did you want to reach?